So here we got a very special type problem because this appeared in Putnam 2000 competition and as well as ISI 2019. And this problem is itself a lemma. So the solution of this is a proof of that lemma. So let's look into the problem. Problem states that f be a polynomial with integer coefficients. It simply means f is over integers, and define a sequence. So we are given here a sequence which is a0, a1, dot dot dot. So the sequence of the integers means the elements are the integer, and a0 is our 0, the value of first element is 0, and for the rest of the element there is a equation which is a n minus n plus 1 equals f of an. So the rest of the elements get defined by this equation, and we have to prove that if there exists a positive integer m for which am is equal to 0, then either a1 equal to 0 or a2 equal to 0. So it simply means that in the sequence there is some element am which is equal to 0. We know this, and we have to prove that either a1 or the a2, any one element is 0. So let's start the solving the problem. So for this I'm going to use a lemma that is very useful to solve a problem, and we already have talked about in our previous video. If a and b are two integers, then a minus b divides p of a minus p of b, and of course a is not equal to b. A and b are distinct integers. So let's see how we can apply this. So here we are given a sequence a0, a1, a2, and somewhere here am and am plus 1. And now we can take a0 minus a1, because we know that a0, a1 are integers. So this divides p of a0 minus p of a1. We can simply say by the above lemma. Since we are given equation that f of an is equal to an plus 1, so we can simply, and one more thing, this f and p are equivalent. We can simply place this p by f because in problem we are given a function f, so we can simply place it by f, no problem. Okay, so we can simply say that f of 0 is nothing but our f of a0 equals a0 plus 1, which is our a1. So here we can put the value a1 and here a2. So we can simply rewrite it as a0 minus a1 divides a1 minus a2, and this divides a2 minus a3, and it will continue up to am minus 1 minus am will divide am minus am plus 1. And we know that am is equal to a0, so we can replace it by its value a0, and am plus 1 equals f of am, which is equal to f of a0, and the f of a0 is equal to a1. We can simply say, so the value of am plus 1 is a1. So we got the final result, which is a0 minus a1 divides a1 minus a2 divides a2 minus a3 up to am minus 1 minus am, and this divides a0 minus a1. And now I'm going to use the divisibility criteria, which is if a divides b, then it simply implies that mod of a is smaller than or equal mod of b. So we can simply say that mod of a0 minus a1 is smaller than or equal a1 minus a2, and up to mod of am minus 1 minus am is smaller than or equal mod of a0 minus a1. And since the edges are same, so we can simply say these all terms are equal. So mod of a0 minus a1 equals a1 minus a2 equals am minus 1 minus am. And now if we try to generalize it, we can say that ai minus ai plus 1 equals mod ai plus 1 minus ai plus 2. So this can be solved in two ways. So the first one is that ai minus ai plus 1 equals ai plus 1 minus ai plus 2. So after solving it, we'll obtain that ai plus 2 equals twice of ai plus 1. And this is something look like a AP, means the arithmetic progress. So we can say that, and if you remember that these all things we already have done in our previous video, I'll give you the link in the description where I do exactly the same way to solve another problem, right? And we know that a0, a1 to am minus 1, am, this is our sequence, and this is AP. So we can say that any mth term in a sequence in a AP, in arithmetic progress, is equal to the first term a0 plus n m minus 1 multiplied by d. D is the difference between two consecutive terms. So mth term is our a0, means 0, equals a0 plus m minus 1 multiplied by d. We can simply cancel these two terms, and we are left with m minus 1 multiplied by d equals 0. So here can be two things, m minus 1 equals 0 or d equals 0. So if we consider this one, d equals 0, because we know that because here we're not sure that m is equal to 1 or not. So if we take this d equals 0, so we can simply say in our arithmetic progress the first term is 0 and the second term must be with the difference of 0. So 0 plus 0 is again 0, and the all elements going to be exactly equals to 0. So it simply tells that if am equal to 0 for any positive m, so a1 equals 0. And second way to solve the equation, this one, is by simply writing it ai plus ai minus ai plus 1 equals minus of ai plus 1 minus ai plus 2. So this simply implies that ai equals ai plus 2. It means if we put the value a0 in place of I, so this is equal to a2. And we know that our a0 is 0, so a2 is equal to 0. So this simply implies that if am equals 0, then a2 is equal to 0. And in these two conditions, this is our first and this is our second, so the only one case is possible. So we can simply say that either a1 equal to 0 or a2 equal to 0.